So this will be our next notes in Unit 5 in Geometry. This is going to be on medians and altitudes of triangles. Last unit we looked at bisectors and how we can use them to find distances on triangles. And now we're going to use these medians and altitudes to help us find distances in triangles. These are very similar, so some of these words you might want to make sure that you highlight them maybe in yellow, or somehow note them in a way that you don't get them confused, because you'll see we'll do something called a centroid and an orthocenter. And if you remember from the last unit, we had an in-center and point of concurrency and those kind of things, so you don't want to confuse them and think one goes with the other and just mess up the question on a quiz or some kind of review. So let's first talk about medians of triangles. Now you can see here's a median. I'll show it to you, starting from the vertex of 1, and it goes across to the midpoint of the other side of the triangle. Okay, so if we look here, a median is a segment with the endpoints being a vertex and the midpoint of the opposite side. So this starts at the vertex, goes across here, but it's right in the middle. So that's called a median. And then if we look further here, we have a truth or a fact. It says every triangle has 3 medians that meet at a point called the centroid. So if we have B, let's go to A first. So A goes across here. It has the midpoint at F. Here we have, starting at B, it comes across midpoint D, and you can see these are midpoints. And then we have E or C coming across here, ends at E at the midpoint. These are the same. And then we have this middle point called a centroid. Okay? And then you can use some different facts about that to help calculate certain things about the triangle. And here we see, if we look at these numbers here, we see that this triangle, ABC, if it has G is the centroid, and then it gives us a distance like BD equals 9, so we know this distance is 9, and these distances are going to be generally different unless it's an equilateral triangle. But here we get BD equals 9. So if we then use that fact, we could use that length and what we know about these centroids and medians and figure out other distances. We'd need a calculation though, or some kind of an equation, and here's the theorem, actually, the centroid theorem. And it says the medians of a triangle intersect at a point called a centroid that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So it's 2/3. Okay? So if you keep that in mind, we'll look at this one here. I'm going to bring this one back in. Okay. And we have BD. This whole thing is 9. Okay. And then we can then figure out, well, what is BG then? And it's 2/3 of BD. So we just plug in 2/3 times 9. We're going to get BG equals 6. So this whole thing is 9. This one would be 6. Then we could say GD is 3. And then we have some calculation or some measurements that we know. Okay. And you can also do something like segment addition, right? I kind of did that down here, where I kind of just filled in 3. But what I'm really doing there, let me move this one down a little bit more so you can see it. So if I know this top one here, BG is 6, I know the total distance is 9. So I can say 6 plus GD is 9, so then I know GD is 3. Okay, so those are just a couple simple calculations that you can do with centroids and medians. Then if we look at the next vocabulary word, we have something called an altitude. Now an altitude is a little bit different than the last one we looked at, the median. This is a segment from a vertex that reaches to the line containing the opposite side and is perpendicular to the line containing that side. Okay, so you'll see here we have this first triangle ABC, this right here. If we were then going to draw from B to the other opposite side, we're not going to worry this time about getting right in the middle. Here we want it to be perpendicular with the other side. So then we have this new line, BD, that is the altitude. What you'll see though, let's say we have another triangle, EFG. So we have this triangle here. What you'll see sometimes is you have to extend it beyond the triangle, okay? And instead of having it inside, we do it perpendicular to the line or the base of that triangle. So here we'd have this one outside, and we'd have this distance here. Okay? And this can help us when you think about what we know about right triangles. So we know we can use Pythagorean theorem, we know we can use things like that to solve for unknowns. And that can help us if we know this side, and we can use, when we know this side, we can also use some of those theorems about right triangles, head or hypotenuse leg and hypotenuse angle to figure out whether triangles are congruent as well. Let me move this back. And there's one more line one more vocabulary I want to show you, and that is something called the orthocenter. Okay, so this one says here the orthocenter. These are the lines containing the altitudes of a triangle. So all those lines are concurrent and intersect at a point called the orthocenter. So if we were going to do triangles for ABC, if we could do each one, do them at a right triangle to this one, right? So we'd put another one in here. Let me just do that real quick, and I'll pause this and come back. So here you can see I did that on the first triangle. I took from a vertex, and I went across to the other line across. I made it at a right triangle. So we'd have A to F, and then here I did C across and did a right triangle, C to E, and then we have this point in the middle, and that is called the orthocenter. This one doesn't go like in half or cut it in half. Instead it goes, it's looking for a perpendicular angle or 90-degree angle with the opposite side. Okay, and you can see here's another example here as well. So let's say we want to take some of these rules about medians and so on and figure out lengths of sides within this triangle. These are all going to be different, because this isn't an equilateral triangle. But if we were just looking at this part of this triangle here, and first thing we'd want to do actually is make sure we have a triangle that is split in, that each one of these sides is the midpoint of the other side, and we look, so this triangle, or this line here, this median comes across, and it is a median because both sides are equal. This one comes across, both sides are equal, and then this one comes across and both sides are equal. So we know we can use what we know about medians to be true. And here we have what we know is this point here, P, and we know that it's 2/3 of the way, right? But what we do know for this one is the smaller side is equal to 2, PD. Okay? And let's say the question is BP equals what? And we know that PD is 2. So this triangle here, we know that we want to know what this whole length is, and we know that this one is 2. But we know that BP, right, is 2/3 the total length, which is BD. Problem is, we don't know the whole length. So how do we use what we know about medians to solve what we don't know, which is that length, that 2/3. Okay, so then what we can do here is we can substitute. So let's start doing some of that. So we know BD is equal to these two segments, BP plus BD. So let's change that, BP, and we know it's all 2/3 times that. So if we just go BP, this first section, plus PD, okay, we got that. Keep going, we know what PD is 2, so we'll substitute. 2. Okay. Then we're going to do distributive property, right? Take 2/3 times that whole thing, leaving BP over here by itself still. So we're going to have 2/3 BP, and that's going to be plus 4/3. So now we're down to this BP equals 2/3 BP plus 4/3. Let me straighten that out there. And then we're going to then minus 2/3 BP from this one, right, using our algebra. And we're going to have 1/3 BP equals 4/3, right? And then if we just do our last one, we could just multiply both sides by 3, and we get BP equals, this cancels, equals 4. So then we know this side is 4. So that's an example of how you can use this theorem, that's what you know about medians, to solve for an unknown. Okay, so we looked at a median and saw how we could solve for unknowns using that idea, that theorem. And now let's look at orthocenters and altitudes. These are going to be a little bit different, but they're going to use some of these ideas that we have learned as we've been going along. Hopefully you can go back to those and maybe even look at them in your notes if you need to. But we're going to graph a triangle, put the coordinates in the coordinate plane, and then we're going to see if we can find the orthocenter of this triangle. Okay. So how we're going to do that is this overall idea with that is first you're going to have to know the coordinates, and we have this triangle FGH, and F is at -2, 4, G is at 4, 4, and then H is at 1, -2. And we're going to go across and make sure this line crosses at a right angle. This one crosses at a right angle, and we'll be good. So the main idea is you want to make sure you keep these in mind whenever we're doing this process, because it's pretty complicated, you're going to see here in a minute. So you find the equation for each altitude, and we're going to start off by doing slope first. So we're going to find out what is the slope of the line that we're starting off. Like example, if we want to go across from G to FH, we got to see what is the slope of FH, and then we know if this is a perpendicular line, it's opposite and inverted for the slope. And then if we go across the other way, this one here, we just need to know we're going this way across to this one. We just need to know the slope of this is opposite and inverted. So let's go ahead and do some of that here. Let me show you. So if we want to know from F, which should be right here, across to GH, we need to find the slope of GH. Okay, and we do that just by plugging in points, right? Because we know the slope is the change of y over the change of x. We're just going to plug that in here. We're going to say we have G is 4 for x and 4 for y, and h is 1 and -2. It doesn't really matter which one you start at. I'm just going to start with G, and I'm going to say 4 minus a -2 for y, and then 4 minus 1, and then we'll end up with 6, 3, or 2. So the slope of this line for GH up here is 2. So if we want to know what the right angle is, and we're just going to draw a line here. So that line coming across, if it's perpendicular, we know the slope of this one, we know the slope of this one should be, if this one is 2, then this one should be -1/2. Okay, just by figuring out the slope of the other line that it's perpendicular to. So if we keep going, and what we'll do is we'll do the next slope for the other line, but next thing we'll do is we'll plug into point slope form to get an equation for it. So then to find the point slope, we just need to know a point on one of these lines. Here we don't know the point, but we know this end point, right, is -2, 4, okay, and we can just plug that in. So we'll do the point slope here. It's going to be -2, 4, and then we're going to plug that in. Y minus 4 is equal -1/2 times x minus a -2. Plugging in these points into that equation, and then when we just do all the solving and everything, we come up with the equation y equals negative 1/2 x plus 3. So we got an equation for the first line. And then, so we're good. We did the slope, we plug into the point slope. We're then going to use this equation once we solve the other equation. We're going to use systems of equations to solve and find out exactly where that point is that they would cross. Okay? So let's show you the next one. I didn't do it on graph paper, I ran out of space, but let me just show you. So the next one we're going to do is, show you the triangle again. So we're going to go to G across the other way to FH. So we're going to go, let me just make sure it's 90, right? We're looking for this point, right? Okay. So that's what to keep in mind. G is 4, 4, and there's our F and the H. So first thing we're going to do is we're going to find the slope of FH. So we have F is negative 2, 4, H is 1, negative 2. The slope is change of y over x, so we plug in, we're just going to use 4 and negative 2. That's going to give us 4 minus a negative 2, or if you just change the signs in it, so it's going to be 6. Okay, and then negative 2 and minus 1, that's going to give us negative 2 plus a negative 1. That gives us, again, 6 over 3, but this time it's a negative 2. So our slope this time is going to be a half. Okay, we then take the other point that would be on this line, because we're going to then write the line. If you remember, we started with G this time, which is 4, 4. So we use that to plug in our points. And we're going to plug in y minus 4. That's from G, which is 4, 4. Put that up here. Okay. And y minus 4 equals 1/2 times x minus 4. We do all our math, and in the end, we get y equals 1/2 x plus 2. Okay. So then we have the two equations. The other one is y equals, y is negative 1/2 x plus 3. So then we should see something in these equations. We should see these are opposites, right? So because they're going across from each other like that, and this triangle has a nice opposite slopes here, we're going to see that the slopes are going to be exactly opposite on these perpendicular lines. So we can use that in systems of equations to solve for some points that we need. And so here we're just going to plug these in. I'm just going to erase these lines. Give me a minute. So then I'm just going to add these two here. And I'm going to get y plus y is 2y. And then look, 1/2 minus a half, or plus a negative half, that's going to be 0. And that equals 5. And then I can just divide by 2. And I'm going to get y equals 5/2. Okay. And then I can use that to plug in and find out what x is equal to. So then if I have y equals 5/2, I just then go back to my equations I have. So y, I'm going to write these down really quick. So y equals 1/2 x plus 2. So then if I take my 5/2 and plug it into this one, 5 over 2, just going to put it up here, equals 1/2 x plus 2. So then I'm going to move minus 2 over here. And so 5/2 minus 2, which is going to be 4 over 2. Okay, I'm just going to make 2 into something that will mess around with this fraction because I'm minusing them. And then I get 1/2. So 1/2 equals 1/2 x. And then I'm going to multiply by 2. Sides. This will cancel, and it'll say 1 equals x. So for this equation, the first one, I have 1 for x and 5/2 for y. So if I then plug it into the other one, let me do on another piece of paper, remembering y is 5/2. If I then just rewrite that equation, y equals negative 1/2 x plus 3. Again, y is 5/2, I solved that, equals negative, this should be negative 1/2 x, and then this is going to be plus 3, and then I'm going to minus it over here, so I want to have 2 on the bottom, so I'm going to make it, instead of 3, 6 halves. I'm going to minus that from both sides. So 5/2 minus 6 halves. This, see if I can bring this up there. So 5/2 minus 6/2, because I'm going to minus 6 halves from both sides. And then I'm going to get negative 1/2 equals negative 1/2 x. This is what I'm left with. Okay, and then I'm just going to multiply by 2. Let me move it down here. Multiply both sides by 2. And there you go. There you go. So then I'm going to make it a negative 2 actually. So I get rid of that thing there. So then I'm going to end up with 1 equals x. So then I can see that they are both the same point. That's perfect. I want 1 and 5/2 for my point. That's for the second one. So then I know where's my orthocenter on this thing right here. We're doing all that. I know that this point right here is 1 and 5/2. So then I just find that 1, and that's like 1.5, right? Or 2.5. That sounds about right. 1, 2, yeah, it's a little bit off, but yeah, you kind of get the idea. So that's how you find an orthocenter on a graph. We'll do probably one more of these in class. Hopefully this makes some sense to you. It's kind of long there, showing you that problem. I hope that wasn't too long. Go ahead and add these notes to your notebook, and I'll see you in class.